Let us revisit the idea again of vectors. A vector has both size and direction. Magnitude, we call it, and direction. We have no trouble generally with the magnitude. It's something like 12 meters, or 13 meters per second, or 18 meters per second squared, or some other set of units. It could be a newtons, a force, but whatever it is, it has magnitude, size, and direction. Let's draw us a coordinate system, and then let's consider a vector that goes in this direction. How do we describe it? The length of this arrow is what we call the magnitude. And since I have no units whatsoever on the axes, neither on the x nor on the y, then I have to tell you what length I'm trying to represent here with this vector. And in this case, I'm simply going to say that it's a vector that's 12 meters long. I want to break it into its components. To break it into its components, what you need to do is think about a light shining down on top of an arrow here. That light projects a shadow onto the x-axis. And it is this length right here that we call the arrow. So let's suppose this vector were called A. Then this arrow represents the x component of A, and we call it A with a sub x. Now think about this same light again, and it's going to shine in this direction. Now it casts a shadow on this axis, which is this long. Here's a shadow coming over here, and it's this long. Since that is on the y-axis, we call that A sub y. So to write our vector, we say A with an arrow on it is equal to a length AX in the x direction. That's what this little hat means on the x. And an AY, distance AY, that's the green line here, in the y direction. That's what we mean with a little hat on the y. And what we're saying is that if you want to get to the point right here that A points to, then you go in the direction AX here, and then in the direction AY here, and that will get you to the same place as if you went in the direction A. That is what the components tell us. How would we represent A along the x-axis and the y-axis? Now we have A equal AX in the x direction, that's in the red. We have AY in the y direction, that's in the blue, but we want to know what these numbers actually are. What is AX and what is AY in terms of what we originally started out with, 12. So let's just think about it as a triangle. If we had a triangle like this, and this was 12, and this were some angle that we'll call theta, then what is the length of this side? We'll simply call it little a and little b. Well, if we take the cosine of theta, we would know that is a over 12. So working this out, that says a is equal to 12 cosine theta. Similarly, if we look at the sine of theta, that would be the opposite over the hypotenuse. We would get b over 12. That would tell us that b is equal to 12 sine theta. Now, we take our vector here. We know that AX becomes 12 cosine theta. AY becomes 12 sine theta, and we rewrite our vector A is equal to 12 cosine theta in the x direction plus 12 sine theta in the y direction. To put a final number to it, let's say that theta is equal to 35 degrees. Then we would have A is equal to 12 cosine 35 degrees in the x direction plus 12 sine 35 degrees in the y direction, that would give us a value of 9.8 in the x direction and 6.9 in the y direction. So we represent the vector A finally as 9.8 in the x direction plus 6.9 in the y direction. That represents this vector, which was 12 meters in this direction of 35 degrees from the x-axis. Now let us look at the problem of adding two vectors, where A is 3 in the x direction plus 4 in the y direction. B is minus 2 in the x direction plus 5 in the y direction. And let's just draw a small picture here and see what those two vectors look like. A is going to be 3 in the x, and then I go 4 in the y, and it looks something like this. B is minus 2 in the x and 5 in the y, so it looks something like this. Now let's add the vectors on one coordinate system and see what they look like. So first of all we do A, here's A, then we do B, here's B, and the resultant vector, which we call R, or anything else, but R equal vector A plus vector B, is a vector that starts where the original vector A started, since we have A plus B, and ends where the head of the final vector is, B. So the resultant, or the addition of those vectors, is what we call R. How do we get it mathematically? We take the two vectors and add them together. So let's write them again. We have A equal 3x plus 4y. We have B is equal minus 2x plus 5y, and we add them together. When we add them together, we get the resultant vector of A plus B, and that is 3 minus 2 is 1.0 in the x direction. These all have little hats on them in the x direction, plus 9.0 in the y direction. And we notice in our picture that really makes sense. If you look at this, it has only about 1 in the x direction and then something like 9 or so in the y direction. So that matches our picture really well, which we would expect. And so now we have R is equal to 1 in the x direction plus 9 in the y. If we want to find the magnitude of R, keep in mind that if we go back, R looks something like this. The magnitude of R is the length of this vector right here, of R itself. And so if we had a triangle in which this was R, and this was its x component, and this was its y component, this is Rx and Ry, not equal to Ax or Bx or Ay, By, this is a new vector, R. It has its own components, and they are 1 in the x direction and 9 in the y. If this were a little triangle where we had C, A, and B, we would know that C squared is equal to A squared plus B squared. So we can solve for the magnitude of R. It's written mathematically like an absolute value symbol, and easily we generally just put an R without the vector sign on it. That's going to be the square root of 1 squared plus 9 squared. This would be the square root of 82, and that would be equal to, rounded off, 9.1. So that would be the magnitude of R. Now suppose we want to find the angle that R makes here with the x-axis. We'll call that angle theta. Well, once again, if we look at the triangle here and look at theta being the angle, we see that the tangent of theta is equal to the y component over the x component. And in our case, that happens to be 9 over 1. To find the angle itself now, we need to take the arctangent of both sides. When we take the arctangent, written tangent minus 1, of the tangent, that returns the argument theta. So theta then, and we would have to take the arctangent of both sides, would be equal to the arctangent of 9 over 1. And rounded off, that turns out to be 84 degrees. So what did we do? We started out with two vectors. We added them together, and we got a new vector R called the resultant. It has an x and it has a y component. We then calculated the magnitude of R right here. Got to a value of 9.1. Then we wanted to see what angle here does R make with the x-axis. We looked at a simple triangle and did the tangent and took the inverse of the tangent to find theta, and we found that vector R has a magnitude of 9.1 and it makes an angle of 84 degrees with the x-axis. And written in standard vector notation, we get R equal 10 in the x direction plus 9 in the y direction.